Good morning, everybody. So I don't want to spend too much time today on this Bohr-Haber cycle. I just want to talk maybe about two things about it, then we'll move on to talking about covalent bonding. One is that the whole cycle we went through was just to see how it is that a lattice energy is calculated on one hand, so that a lattice energy itself isn't directly observed, but it's calculated through knowing things like enthalpies of formation of sodium gas, chlorine gas, and then their ionization energies to go to sodium plus, the electron affinity to go to Cl minus, and then finally the lattice energy just kind of falls out from like a Hess's law summation. One other way to think about this is if you start with like sodium solid, is to think, okay, if I have some energy here where energy is going to, if I increase energy, it's going to go up. Then we have to have sodium absorb energy to go to sodium gas. So in terms of a diagram. So energy has to be absorbed to go from the solid phase of a substance to the gas phase of a substance. And then we might be imagining here that we have Cl2 in the gas phase, just kind of like elemental chlorine. So you might be asking the question kind of like, why does NaCl solid form? Why don't we just have the elements of sodium and chlorine predominate for these two elements? Well, we're going to see that it's because of what they can form and then how what's formed can interact with each other. And so if we sort of take solid to gas for sodium, so we still have Cl2 gas, and then we take our Cl2 gas, we're just going to have half of it for the one Cl atom here. And so we have a half Cl2. Then we have to break that bond between the two chlorine atoms. And bond energies are always positive, meaning it takes energy to break bonds. So we have to absorb some more energy to form sodium gas plus the chlorine atom separated from the molecule. So we have like maybe half a mole of chlorine of Cl2. So we have to break that bond between the two chlorine atoms. So that takes energy as well. And then we have to ionize the electron off the sodium. We have to go to sodium plus. Ionization energies of elements are always positive. Lowest for the alkali from left to right, but still requires a positive amount of energy to be absorbed. So we go uphill in energy again to go up to sodium plus as a gaseous ion. We still have chlorine gas, and then chlorine can accept that electron that's given off by sodium, so sodium loses an electron. We can have that electron absorbed by chlorine. That's the only step here that's actually negative. So for the halogens, they have the most negative electron affinities. And so then this comes downhill. So here we have sodium plus as a gaseous ion, and then we have Cl minus as a gaseous ion. And so just the electron affinity and like the ionization energies taken together for sodium and chlorine, that's not enough energy for this process to take place. So we don't make gaseous ions here between sodium and chlorine. We don't stop here. They then are attracted together. So they then form sodium chloride solid. And so then sodium chloride solid comes all the way down to here in terms of its lattice energy due to the electrostatic force of attraction between the plus and the minus. So we form our sodium chloride solid. So the full picture on why like NaCl forms and predominates, like why we find sodium chloride in plus minus form in nature and not sodium, metal, chlorine, elemental chlorine, is because of the energy landscape here. It's because it's overall downhill in energy from the elements to form NaCl. So because we have a drop in energy compared to where we started, this drop in energy here is why ultimately the NaCl forms as the plus minus. Now, a few things that you could take away from this are you can start thinking, well, why don't we go, Na minus Cl plus? Like, why don't we flip this? Why don't we put the minus on sodium? And if you start thinking about how much energy it takes to go to, like, say, chlorine plus instead of chlorine minus, it takes more energy to ionize electron off of chlorine. So you have even more energy to go uphill if we wanted to take the electron off of chlorine. We don't get the same energy back from sodium. So in terms of like where our ion energies would be way higher. And then the force of attraction of a plus minus versus a minus plus, probably pretty similar. So the lattice energy probably wouldn't be too different. But we'd end up with the sodium minus chlorine plus higher in energy relative to the elements. So it kind of gets us maybe into a thought process that what forms isn't necessarily going to form just because it's stable. It's going to form because it's like more stable than other options. And so forming this is more stable than our elements. So it's more stable than the elements we started with. That's why it predominates. And then why Na plus Cl minus forms is because it's more stable than some other combination of ions. You could say, well, why not sodium 2 plus? Because doesn't 2 plus have a stronger lattice energy than a 1 plus minus 1? The answer is, well, you got to add another 5,000 kJs per mole of energy to get that second electron off of sodium. You're not getting that back in terms of lattice energy. So you can start to think about just the thought process of what happens being the most stable of all the options that are possible, and trying to understand what some of those processes look like. Just to show you another example of this would be like magnesium chloride. So magnesium, same kind of picture, goes from solid to gas, and then we take our Cl2 and break it to chlorine, and we start ionizing magnesium all the way to 2+. It does take a fair amount of energy to go from Mg to Mg+, Mg2+, but we're going to get that energy back from our lattice energy later. And so then we put the electron onto chlorine, go downhill in energy to make Cl-, and then we finally get that lattice energy with a +2 -1 that's relatively high. And then again, our MgCl2 more stable than the pairing of the elements. So we form a compound MgCl2 because it's more stable than the elements that we could have stuck with if it wasn't more stable. And so probably the main walkaway for lattice energies with this picture here is this is how they're calculated. But then the bigger picture lattice energies, I think, is just the idea that as you change the charges, you can change the lattice energy. So the higher the magnitudes of charge, the stronger the attractive force, the stronger the lattice energy. And then likewise, the smaller the ions, the better. So whenever you're changing charge, the smaller you can make the ions, the closer they are together. That makes for a greater attraction, hence a greater lattice energy. From here, get into covalent bonding next time. All right, have a great day. Okay, so that's kind of it for ionic bonding. So the rest of the chapter deals predominantly with covalent bonding. So trying to understand the types of bonds that form between nuclei where they're sharing electrons. And so on the simplest molecule would be something like H2. So hydrogen has a single bond between the two hydrogen atoms. Each hydrogen has one valence electron. So those one valence electrons of hydrogen can sort of simultaneously overlap with each other or just interact with each other such that the two electrons are attracted to both of the nuclei. So it's the electron nuclear attraction that allows bonds to form kind of in the first place. So it's kind of recognizing that a lot of times we write electrons as dots, but they're negative particles that are being pulled into the positive nuclei of the atoms. And it again kind of becomes a question of, is this more stable than just staying as two hydrogens? The answer is yes for this molecule. That if you think, and this is a picture that comes up in chapter 9, but if you think of the energy of two hydrogens that are separated from each other compared to the energy of the hydrogens that are bonded together, you get sort of a lower energy when you pair those atoms together and make a bond. And so for bonds, it always takes energy to break a bond. And then for why one bond forms versus another is usually just a question of, well, which one adds the most stability for the atoms. So what we're going to try to do as we go along is just understand ways of trying to sketch Lewis structures for thinking of how these electrons might overlap or interact with each other. In some cases, we can think of dot structures. So sometimes we can think just kind of like hydrogen has one valence electron, another hydrogen has another. So the best way that they can sort of pair up together is to make a single bond. If there's a driving force, it might be towards a noble gas configuration. So the nearest noble gas to hydrogen is helium. So helium has two valence electrons. And so each hydrogen kind of ends up simultaneously satisfying a configuration that looks like helium by sharing those two electrons. And then you might wonder and say, well, why don't we just do something like H plus and H minus, like form an ionic compound here? And the answer just comes down to hydrogen has a huge ionization energy. It takes too much energy to take an electron off of hydrogen. Electron affinities aren't good enough to put the electron onto the other hydrogen, so this just isn't something that's possible for most of our non-metallic elements. Ionic compounds are going to be better when we have metals and nonmetals, where metals have low ionization energies. Nonmetals on the far right side of the periodic table have favorable electron affinities. But for the elements in the middle, hydrogen, and our main group elements, like our 2p elements, it's going to be sharing electrons through things like covalent bonding. So if we imagine the hydrogen, again, one valence electron, fluorine has 7 valence electrons, we can then simultaneously give each of those their nearest noble gas configuration by making a single bond. Water has, oxygen has 6 valence electrons, each of the hydrogens has 1. So we can pair those up with single bonds as well. Nitrogen, likewise, has 3 valence electrons. or excuse me, 5 valence electrons, 3 kind of unpaired electrons that then pair up with hydrogen. And then carbon, I think, was a little bit peculiar where we might have been thinking on a dot structure, and this was like a valid dot structure. I think if you write this as a dot structure of carbon, I don't think that's wrong. But then there was this other dot structure where we wrote it this way here, and thinking of this as your dot structure of carbon just makes it easier to make things like CH4. So it's really just for the likeliness of making carbon with 4 single bonds, where you might sketch a dot structure with 4 dots on it. And so with carbon, 4 valence electrons pairs up with 4 hydrogens. And so if you notice here, all of these molecules have obviously a different number of hydrogens, but it's just because they each have like a different ability to pair up with hydrogen. So fluorine just 1, water 2, ammonia 3, methane 4. There's a concept of formal charge. Yes?
With the H2O, does it mean the next stable form would be H6O?
Say that again?
With the H2O, the 2 valence electrons going for the hydrogen.
Yeah.
The next form of stable form for the oxygen, would it be H6O?
H6O, I don't understand how you would get that.
Like those are 4.
Oh, you mean like taking like a hydrogen onto each of these like that?
Right.
No, and we'll see. I think what you end up having a problem with is those electrons are in an orbital. Like in some of the orbital pictures comes up in chapter 9, but if you have an orbital here, it's not going to want to separate into 2 separate like bonds. So like a lone pair is fine, you know. So like a lone pair of electrons is actually a good thing for an atom, and we're going to see a lot of times things like water, ammonia, fluorine, they keep their lone pairs and they're not unstable. So it's not unstable to have electron pairs that aren't bonded with other elements. And so I think on one hand you can see having an unpaired electron makes it easy for it to find another electron to pair up with, but having like an electron pair is actually okay. And one of the ways that we can see sort of if a structure might make sense, and this will be something we calculate a lot of times, is something called a formal charge. So a formal charge is sort of what is the charge of an atom if we assume that these bonds are equally shared? So if we I'm just going to resketch ammonia just to make this a little bit bigger. And so if we imagine ammonia having those 5 electrons closest towards it, and hydrogen each have 1 electron closest towards the hydrogen, if I cut each of these bonds like in half, and almost maybe like think of drawing a box around each of the atoms, notice I'm going to keep the lone pair electrons on the atom they reside on, and then I'm going to break the bonding pair electrons kind of in half and kind of say on average, if these bonds are equally shared, then 1 electron's closer to hydrogen, another electron's closer to nitrogen. And then the concept of formal charge is thinking, well, what would the charge of the atom in the box be with that count of electrons? Like if I had nitrogen with 5 electrons closest towards it, what would its charge be? And the answer would be neutral. That's just an ordinary neutral nitrogen atom. Well, why is that? Well, nitrogen only has 5 valence electrons, and it's surrounded by 5 valence electrons here. So that would be an uncharged atom. And so if you notice that carbon has 4 valence electrons, and it's surrounded by 4 valence electrons. If you cut the bonds in half, it would be surrounded by 4 valence electrons. So its charge here is also neutral in terms of what we call a formal charge. So a formal charge is you just assume the covalent bonds are equally shared, you cut the electrons in half. This doesn't change like our octet rule picture. In fact, I don't think I've used the word octet rule yet, but the octet rule is kind of the noble gas rule. It's the idea that an atom kind of wants to have the configuration of electrons that looks like its nearest noble gas, like neon for carbon, helium for hydrogen. And so carbon still has 8 electrons surrounding it. So when you think of carbon's sort of octet, you're still thinking it has 8 electrons surrounding it. But in formal charge, we're breaking the bonds in half. And so there's a lot of examples of formal charge that will come up. So we'll see some more examples to reinforce the idea of formal charge. I just want to introduce it here and to show that fluorine, oxygen, and the nitrogen and carbon here are all neutral. So they're all neutral in charge. So satisfying the octet rule being neutral in charge is something we're going to see for a lot of different compounds, is something that is like a characteristic of those compounds being stable.
Like oxygen, carbon also has a case, and then 2 remain unstable.
You mean in like this structure here?
Right, 2 are there and 2.
Yeah.
Why is it coming sequence?
Well, yeah, so I think that's a good question. I mean, I think on one hand, we're trying to almost say, okay, if CH4 exists but CH2 doesn't exist, then probably a reason why is that CH4 is just trying to satisfy the octet rule. So like if you come up with a structure that looks like this, so if you leave the lone pair on carbon, and you come up with a structure like this is actually an interesting compound that people have researched a lot, but it's not like stable enough. You're not gonna like put that in a bottle. But it does exist. It's a stable enough compound that exists. You can characterize it and try to study it, and people have done so. But it's not stable like water is, where you can just like bottle it. And so the reason why is that you have these electrons here that can actually then say, okay, here we're going to separate into two different orbitals, and then we'll pair up with two different hydrogens after that process. So then CH4 predominates here because it allows the carbon to satisfy the octet rule. So if we go back to this structure here, oops. So this structure here, notice that carbon only has 6 electrons surrounding it. So carbon can have 8 electrons surrounding it. So if it makes 2 more bonds, then it gets those 8 electrons. Yeah, and so then it can do it like a lot of, like I don't want to get too bogged down on things that can do it, but like we had seen the picture of like having an oxygen pair up for like formaldehyde does the trick as well. So we can keep those 2 electrons kind of where they are, although not exactly. I mean, we have to see a bonding model for these molecules that comes up in chapter 9 a little bit to see how the orbitals interact with these atoms to make these types of bonds. So we'll see some bonding pictures when we get into chapter 9. And you may have seen some of those. It's like hybrid orbital theory, if you recall seeing some of that stuff. And so for now, the question kind of becomes, how do we know when we can make double bonds? Well, one of the things for like carbon and oxygen making CO2 is kind of thinking, okay, well, what if we pair up, you just have to picture the different electrons pairing up. Maybe if I do it, so we just want to take our electrons and pair them up together. We can make double bonds on either side of the carbon. So CO2 would have 2 double bonds. So the double bonds here have, instead of 2 electrons being shared, they have 4 electrons being shared between each of the nuclei there. So we have 4 bonding electrons. So 4 bonding electrons. A single bond only has 2 bonding electrons. And so the double bond, those electrons like glue, they're holding the nuclei together. They're negative particles that are pulling the nuclei together. So one concept that we're going to see is that if you compare a single bond between 2 atoms versus a double bond between 2 atoms versus a triple bond between 2 atoms, that having more electrons in the bond serves to act as more glue. So we're going to pull those nuclei closer together. So notice that we go to a decreasing bond length for the nitrogen-nitrogen bond when we have more bonding electrons. So bonding electrons, these are negative particles. So the negative particles are bringing the nuclei closer together, the more of them that we have. So then nitrogen, in terms of N2, so we have nitrogen has 3 unpaired electrons each. So if those electrons are able to overlap with each other, pair up, then we can picture forming a triple bond. So a triple bond here does a couple things. One, it allows each of the nitrogens to have 8 electrons surrounding it, so that it comes up kind of with that noble gas count of electrons. And then it also allows each nitrogen to maintain that 0 formal charge. So think about the formal charge of nitrogen. So nitrogen should have 5 electrons surrounding it for neutral charge, and it does here. So each of these nitrogens are neutral in charge. Nitrogen's uncharged, and both of the nitrogens, like N2 is uncharged. And so if one nitrogen's -1, the other one would have to be like +1. And they're both the same. So I mean, if we just look at nitrogen, we'd have to really conclude, well, if one's 0, the other has to be 0. That's the only really charge that's possible, because I'm looking at these nitrogens saying, well, they're the same. There's nothing different about them. And so since N2 is a neutral molecule, of course the nitrogens have to be neutral in charge. Almost kind of comes back to oxidation numbers, where the oxidation numbers for an element, for a pure element, are 0 by definition. We see that here with N2. If we think about formal charge in CO2, for CO2, we see that the oxygen still has 6 electrons closest to it. You ever have that moment where you're like, oh boy, I'm losing my voice? Okay, so oxygen should have 6 electrons surrounding it, and it does.
How are we able to find there's only one line with 2 lines with 3 lines in an N2?
Oh, so good question again. Still, I was like, if you just want to do all the talking for the rest of the class, it'd be great, because I'm like, man. So how do you get this here? The answer is through a different molecule. So you would get it through a different type of compound that just would exist with a nitrogen-nitrogen double bond. You would get the single bond just for a different compound. So like if you had something like NH2, NH2, that this molecule here would exist with a single bond between the two nitrogens, kind of like how CH3 exists with a single bond between the two carbons. And so that's like, so you're looking at a different molecule. So you wouldn't have N2 just as an ordinary molecule. So if you had like NH, then that would have a double bond. And so then a molecule like this would then have a slightly shorter double bond. So definitely a good question. So it's not just a simple N2 molecule changing its bond length. But the concept, or the idea is, if we have different types of structures where one has a triple bond, one has a double bond, one has a single bond between the two atoms, the triple bond is going to be the shorter. Okay, so this question here just kind of goes back to ionic bonding, just for a quick little kind of rehash of lattice energies. Just take maybe a minute to try to think of which compounds here have the greatest lattice energy. Okay, so do you guys all agree mostly that it's B? So that smaller ions with the same charge, the better. So the more attractive force they'd have between each other, the more energy it would take to separate them. So LiF would be greater than CSI. And then NaCl versus MgS being greater in charge for magnesium 2 plus, magnesium 2 minus. I don't even need to think about the size difference between the ions. It's really just the charge difference that plays the big role here. So being double for each of the ions in terms of their charges would make the lattice energy of MgS about a factor of 4 higher than NaCl. Okay, so let's talk about bond polarity. So let's talk about the difference between a polar versus a non-polar bond. And so we can contrast this also with ionic bonding. So like if we look at a non-polar bond, it's where the electrons are shared equally between the atoms. So what that would mean is if we take a fluorine molecule, like an F2, so for F2, we're picturing sort of each fluorine with one electron that's unpaired. Each fluorine's just one electron away from that noble gas configuration. So we come up with the Lewis structure with a single bond between the two fluorines. You might recall that fluorine's the most electronegative element, or excuse me, the most, from left to right, it has a really high effective charge, and it has a particularly favorable electron affinity. And so what that means is it has a really strongly positive nuclei. And you can imagine that that nucleus wants to pull electrons towards itself. That's what positive charge does. Positive charge says, well, if I see negative particles, I'm going to try to pull them closer towards my nucleus. And then the other fluorine's going to do exactly the same thing, because it's the exact same nucleus. So it's going to try to pull those electrons closer towards itself. So we have a tug of war between two atoms or two people that are equally strong on those electrons. So the electrons are pulled equally, so therefore they end up being equally shared. And so in the concept of formal charge, or the sharing of those electrons, it's going to be exactly equally shared. So that each of these atoms here have to be 0 in charge, both in terms of their formal charge. So we'd say the formal charge of fluorine would be 0, but then the actual charges are actually 0 as well. So that this is representative of the true charge. So the true charge has to be 0 as well, because there's no way for one of the fluorines to pick up a negative charge, because it would be at the expense of the other going positive, and the other nuclei would be like, what are you doing? I want the electrons too. So we set up a tug of war where the two atoms are equally shared, sharing those electrons. Now if you contrast this with LiF, which is ionic, then you set up a situation where you can imagine where maybe this tries to form. So maybe lithium fluorine says, well, let's share those electrons. And fluorine says, well, remember how my nucleus is more positive than yours is, so we have this big positive charge. It's going to pull these electrons in more closely towards itself, and then lithium loses the fight. So lithium loses the fight completely. So lithium can't pull for those electrons at all, so they permanently go over to fluorine, make F minus. So we pick up a fluorine with a minus charge, lithium with a positive charge. And so here we just set up a situation where it's so easy for lithium to lose its electron comparatively, and it's so stable once it loses it that it picks up that plus minus electrostatic force of attraction. So plus minus predominates for something like LiF. Well, for something like hydrogen fluoride, now again, hydrogen is particularly different from the other alkali metals, or from the alkali metals, it's not a metal. So what makes hydrogen different is that 1300 kJ per mole ionization energy compared to about 500 or less for the other alkali metals, or for the alkali metals. And so hydrogen wants to keep a hold of that electron when we make the HF bond, but it doesn't completely keep a hold of the electron. So the bonding pair electrons are going to shade towards the fluorine. So the electron pairs are just going to be a little closer to fluorine than they are hydrogen. What this does is it allows fluorine to pick up a partial negative charge, and it allows hydrogen to go positive in charge with some partial charge. In a few moments, we can actually go through and calculate to what degree those charges are. There's actually a fairly interesting calculation you can do to calculate, well, what do we mean by partial? Well, one thing that we mean is that by being partially negative, it's somewhere between 0 to 1 electron. And then it's negative for the fluorine. And so if you imagine, if it's ionic, it's -1. Like for LiF, it's -1 electron. And so for the fluorine and HF, it's going to be somewhere between 0 is what it would be if it were completely nonpolar, or it's going to be somewhere up to -1 electron. So maybe about -half an electron. So -half instead of -1 if it's fully ionic, instead of 0 if it's completely equally shared. But now let's also then come back to the idea of formal charge. So the idea of formal charge is so that the fluorine, in terms of a formal charge, is equal to 0. So the formal charge of fluorine remains to be 0 in HF, but the true charge is now different. The true charge is negative due to that dipole or the polarity, or if you think of the electronegativity, the ability of fluorine to shade those electrons closer towards itself. So a polar covalent bond is one where the atoms attract the electrons with a greater force than the other nuclei attract those electrons. So fluorine's more strongly positive than hydrogen is. The bonding pair electrons shade towards the fluorine atom, allowing it to adopt a partial negative charge. Now it's just not strong enough, and the hydrogen's also not weak enough that the hydrogen just doesn't completely give up those electrons. So H doesn't go to +1, F doesn't quite go to -1. Okay, so here's kind of a picture of F2 versus HF, where we're going more plus-minus for LiF, 0, 0 for F2, and then a partial plus, a partial minus for H and F. So if we look at an electronegativity chart, we can get a sense for, okay, for different nuclei, what's their pull for electrons and bonds? And so fluorine turns out to be the most electronegative element, and I don't think this necessarily is, it's maybe kind of obvious. What you're really thinking of for the ability of a nuclei to pull electrons towards itself is for it to be relatively high in positive charge. If you think of effective charge, iodine's actually the most highly charged element in terms of effective nuclear charge for things that form bonds. So notice we skip the noble gases because they don't form bonds here. And so the noble gases aren't really participating in bonds. Electronegativity is for atoms and bonds, which of the atoms has a stronger pull for electrons towards itself. Fluorine wins the fight, not because it has the highest effective charge, but because it has relatively high effective charge, but then is really small. So remember, being small for charge is good. So if we want to pull charge towards a particle, being smaller is better. So being small with a relatively high effective charge is what makes fluorine particularly good for being the most electronegative element. Now, if you go back to a concept from chapter 4, remember when we were assigning oxidation numbers, we had like molecules like OF2, and one of the rules for oxidation numbers is that fluorine goes negative and then oxygen adjusts itself accordingly to be positive. So from an oxidation number perspective, the oxidation number of oxygen would be +2, fluorine from -1. This is from chapter 4 on oxidation numbers. Well, what you can see here, the reason why is that fluorine's more electronegative. It wants to keep the charge. Oxygen's less electronegative. It can go positive. So fluorine wants to have the most negative charge for all the elements in the periodic table. The other atoms, therefore, have to adjust accordingly. So something like OF2 would be +2 for oxygen, -1 for fluorine. Now, in terms of this chapter here, you can see like HF is pretty different in electronegativities. The greater the difference in electronegativities, the more polar the bond. So if we look at two fluorines together, so despite having two electronegative elements, the difference in electronegativity is 0. So if two elements happen to have the same electronegativities, they're bonded together, then that's not really going to be a polar bond. We need there to be some difference in electronegativity. So the further we get away from fluorine, if you imagine an OF bond, it's polar, but not particularly polar compared to like an NF bond versus CF bond. The CF bond here of these three is the most polar. The FF bond, of course, would be the least polar. And so we're just increasing electronegativity the further we separate the elements, because therefore we get a greater electronegativity. So see that our electronegativity increases towards fluorine, both up a column and from left to right. And so if we get a greater difference in electronegativity, if we get to be so great, then it just becomes ionic. So if you notice, your alkali metals have electronegativities that are below 1, or 1 or below, and then fluorine particularly high. So you get a big difference in electronegativity, then you're going to have a substance that behaves more like an ionic substance. And so now, the textbook used to put limits. It used to say if you have an electronegativity difference of 2, then that would be ionic. I think it was like 0.4 to 1.9 was polar covalent. But if you use those rules, you get some compounds backwards. Like CSI is really, truly ionic. But if you look at the difference between like iodine and cesium, you might call that compound to be polar covalent. So I think those limits don't really mean much. So I think we go back to the same idea. Metal, non-metal is going to be ionic. And then non-metallic elements, if you notice, the non-metallic elements have electronegativity between 2.1 and 4. So if you have some non-metallic elements bonding with each other, then it either has to be nonpolar, just where the electronegativities are the same, or the atoms are the same, like in F2, and the difference is 0, or the bonds are going to be polar, and the greater they're separated, the more polar. Okay, so one of the things you can do with diatomic molecules is you can actually calculate the charges that will reside on the atoms if you know the bond length of the molecule, and then you can also either calculate or know something called the dipole moment. So the dipole moment mu is equal to the charge that's being separated by some distance. So Q times R, where Q is just the magnitudes of charge that are being separated by the two atoms by their distance of separation, by their bond distance R. And so dipole moments are experimentally observable. And so you can determine dipole moments through experiments. You can determine bond lengths through experiment as well. And then you can also just look at the electronegativity difference between HF, Cl, Br, and I. Of course, HF has the greatest electronegativity difference. Probably not going to be so surprised to see that it has the greatest dipole moment. Therefore, we would be calling HF the most polar. So the most polar difference from the greatest difference of electronegativity. As you go down the halogen group, you're getting closer towards hydrogen's electronegativity, so you're going to a smaller electronegativity difference. But notice that H is 2.1, iodine's 2.5 from the previous page. And so iodine still picks up that negative charge. So if we're looking at our bond here, iodine still becomes the partial negative, hydrogen being the partial positive. And so the more electronegative element, it's picking up that negative charge, and it's just going to be picking up presumably less charge due to being less polar. So it has a smaller dipole moment, a lower difference in electronegativity. Therefore, of these four, it's the least polar. Okay, now you would imagine being less polar would probably mean less charge residing on the atoms. Being more polar would probably mean that those partial magnitudes of charge are greater. So if you're thinking of these partial magnitudes in charge, the deltas, or you might call these plus, and minus Q. So plus and minus Q, the partial charges, that the greater the electronegativity difference, the more polar, the greater the magnitudes of those charges. And so something you can is actually run through a calculation to calculate the charges. It kind of almost becomes a proof of concept of if we're saying that in something like HF or HI, that those bonds are polar to some extent and that the charges are somewhere between 0 and -1 electrons, we should be able to calculate what that charge is for these molecules and kind of see just how negative these charges are to get a sense of what we really mean by a partial charge. And so if we take the bond length and dipole moment of HF, so 0.92 angstrom, 1.82 debye, we have a couple conversions we need to make here, and that is that this is the dipole moment mu. So mu is the dipole moment, the Greek letter mu, and then the debye is what this is. It's named for Peter Debye. So the debye unit is just equal to some SI units of coulombs times meters. If you think of mu being equal to Q times R, it's your Q in coulombs times the bond length in meters gives you your dipole moment in coulomb meters. And so then we have a non-SI unit that's commonly used for the unit of dipole moments called the debye, symbolized with a capital D. And so here we're going to try to calculate the charge on fluorine in the molecule of hydrogen fluoride given this information here. So we're also given the charge of an electron is 1.6 times 10 to the minus 19 coulombs, and we're given that dipole to coulomb meter, debye to coulomb meter conversion. Yeah. Yeah, well, we'll work them out. So let's try to piece them together. So let's try to think of how we take the dipole moment is Q times R. We're trying to solve for the charge on fluorine. So we're trying to solve for Q. So we're going to take mu divided by R. And then we're just going to have to account for our units as we kind of go in the problem. And so when we go to plug in our dipole moment, so this is our dipole moment here. So we go 1.82. And then we debye, then we divide by 0.92 angstrom. The first thing I think we should recognize is that these units don't necessarily cancel each other out. So we need to do some conversions to see how the units cancel. The other thing I think if we're thinking, if we do the math here, that's going to be a charge that's greater than 1 electron, which would be like even more ionic than ionic. It's like if we're thinking of the actual charges here we would expect for HF, which we've already talked about this, but just to rehash it, it's that the charge is going to be partially negative, somewhere between 0 and 1 electron. So it should be less than -1 electron in terms of the charge on fluorine, and it should be negative. So charge on fluorine should be negative, not positive. The hydrogen is going to be positive, so we can roll out half the answers already. But then if we just do this math here, we're going to get like -2 electrons or somewhere in that ballpark. And that would mean we have like H plus 2, which seems impossible, and F minus 2. So we have to do some conversions here. So what we have to do is just apply that conversion here. So 1D is equal to 3.34 times 10 to the minus 30 coulomb meters. So notice it's minus 30. Like we have Planck's constant is to the minus 34. So sometimes we write minus 34 here, but it's just to the minus 30. And then once you see the meter here, you kind of get clued in, okay, I have to convert angstrom. So 1 angstrom is just a 10 to the minus 10 meter. So 10 to the minus 10. So 0.92 times 10 to the minus 10 meters is the bond length. And so then that allows angstrom to cancel, then meters to cancel. My debye unit canceled. And then if I stop and calculate here, I mean, I could do the next conversion, but you may not understand why I'm doing the conversion. So let's just calculate it here, get the charge in coulombs, and then try to think of why we do the next step the way we do it. And so we go 1.82 times 3.34 times 10 to the minus 30, divide by 0.92 e to the minus 10. So I get 6.0 0.61 times 10 to the minus 20 coulombs. So the last step we need to think about is kind of, well, this is a charge on one fluorine atom. When you think of like plus minus, for like sodium chloride, +1, -1, it's +1 electron, -1 electron. If we were to calculate the charge on chlorine and sodium chloride, we should get that the charge on chlorine per atom would just be the charge of 1 electron. So it would just be minus 1.6 times 10 to the minus 19 coulombs. And so the last thing that we need to do is just use the charge of 1 electron to convert into electron charge units, to kind of count, like, well, what's the fraction of an electron that this charge represents? And so then this is why we're using the 1.602 times 10 to the minus 19 coulombs per electron. So it lets you calculate the plus or minus. And the only thing that's confusing is when you say +1, -1 for something, you're really saying +1 electron, -1 electron. And so then this here will allow us to calculate the actual fraction of the electron that this charge represents. So we divide by 1.602, e to the minus 19, and it's 0.41. And so remember how we said the charge for a partial charge would be somewhere between 0 and 1. And then we're here with really, pretty much the most polar you can be and not be ionic is HF. Because if you look at the electronegativity chart, most of your nonmetals are between 2.1 and 4. So this is about as polar as you're getting, and it's about half. It's getting close to half an electron being shared between, half a unit of charge being shared between those two nuclei. And so our charge on fluorine would be minus 0.41 electrons, and the hydrogen charge would be partial positive, plus 0.41 electrons. So the Q we get is just the plus and minus that's being separated. So it's the plus charge in the positive atom, the minus charge in the minus atom. And then we're just looking at the negativities. We're thinking about the charges that we began with in our Lewis structure being neutral, so 0 in terms of formal. Polarity kicks in, more negative on the more electronegative fluorine atom. Okay, so we could repeat this. Like you could see if you do HF, a little less polar, guess what the charges are? A little bit lower. I think it's 0.27 units of charge. If you go to HBr, it's like 0.14. I think I've done the calculation enough that I remember that's about 0.14, and it's like 0.07 for the charges in HI. So as you're dropping in polarity, the magnitudes of charge are dropping. And so there's a lot that, like sometimes you see these numbers and it's, like on one hand it's just a number, but what the meaning of this charge is that adds some electrostatic attraction in this molecule that strengthens that HF bond. You guys remember HF is not one of the 7 strong acids. It's not a strong acid because of that electronegativity between these two atoms, keeping them kind of locked together, making that bond stronger. And so the sort of electrostatic attraction that those two ions then get based on their charges strengthens that bond. So our bond strength of HF is actually a lot stronger than we would expect otherwise. And so there's ramifications of this electronegativity difference in terms of the acid behavior of HF in solution. And the same thing with like polarity. Like we're going to see polar molecules behave differently than nonpolar molecules. Once we get into chapter 9, we'll start to think about molecules. Is the molecule polar? Is the molecule nonpolar? When we start thinking of like water versus CO2, big difference between their properties because one of them is polar water and CO2 is nonpolar. Yeah. For like the formal charge for the charge that we're just calculating on the previous page, I'm sure you could go above 1 on some type of compounds, but and it would just have to be something other than hydrogen. But I'd have to think of an example where we go above 1. I'm sure you can. Yeah. You would just have to have like I might search for an example and see, but but in a way. The previous page is like a proof of concept. It's like trying to prove, I think, the idea or support the idea of what we mean by partial charges. And so we're saying a polar bond has partially charged atoms. We're kind of seeing probably somewhere around like 0.1 to 0.2 electrons for an ordinary polar bond. If you're really a polar bond, maybe up to about 0.4 units of charge. Okay. So formal charge is a charge an atom would bear if the bonds are 100% covalent. So perfectly covalent is the idea of formal charges. And then, but the real actual charges come from the concept of bond polarity and electronegativity differences. So for diatomic molecules, what we try to do for diatomics, and this actually doesn't always become the driving force for bigger molecules that we'll see, is that we try to satisfy the octet rule as kind of like a rule of thumb. So for a diatomic molecule, we start thinking here, how do we satisfy the octet rule for carbon and oxygen? One of the things we'll start doing is thinking of how many valence electrons the atoms have. So the valence count should be the electrons shown in the Lewis structure. So carbon has 4, oxygen has 6. So that's 10 total electrons. And so then if you're trying to satisfy the octet rule for both these atoms, if you just use a double bond, you're going to need 12 electrons. So we need 12 electrons to satisfy the octet rules for both these atoms. So a double bond's not going to work. So what if we go to a triple bond? So it's kind of like starting, you can imagine starting single. Single would have been like F2, where we would have had the single bond, 3 sets of lone pairs on each atom, way too many electrons. So maybe we had ruled this one out in our head already, that this is just way too many electrons for CO. CO with the double bond, again, too many electrons, that would be 12 electrons. And then for 10 electrons, it's going to be like N2 with a triple bond. And now with a triple bond, let's think about our formal charges of these atoms. And let's break that triple bond in half. So again, we're just breaking it in half to say on average what's the charge on each of the atoms if we do that task. And so breaking the bonds in half, do you notice that carbon picks up actually negative charge here? So carbon should have 4 electrons surrounding it for a neutral charge, and it has 5 electrons closer to it here, giving it a -1 formal charge. And then oxygen should have 6 electrons closest to it. It only has 5 in this structure here, so it goes positive. And this is actually okay. This is the Lewis structure of CO. And so carbon monoxide is particularly bad at binding to things like hemoglobin because the carbon actually binds and it irreversibly binds. And it binds in a different way. Usually you want O2 to bind to your hemoglobin. And O2, the oxygen actually would bind reversibly, but the carbon, through its nature of bonding with iron and hemoglobin, is an irreversible bond. So if you have carbon monoxide poisoning, you need your hemoglobin to be remade and replenished by your body to get rid of the CO-infected hemoglobin. So that CO is effectively never coming off. And it's because of the nature of the bonding. You can bind through the carbon because of that negative charge residing on that carbon atom. Now, it's an interesting problem, maybe not interesting enough to do here, but I think one of the practice quizzes has the dipole moment, bond length of CO. The actual charge that resides on carbon isn't quite -1. You can think electronegativity should kick in. The bonding pair electrons are going to slant towards the oxygen, but it still keeps that positive charge. So it still is overall positive, but maybe not as positive as +1. And so you can still think of bond electronegativity kind of changing the charges from where we're predicting them, but carbon still keeps that negative charge. And I feel like if carbon didn't keep the negative charge, we might go with a different Lewis structure. So carbon saying negative is closer towards this Lewis structure than maybe other Lewis structures you might try to write. If we go NO+, how do we deal with positive charges when we're doing structures? Well, just think of our count for nitrogen should have 5 valence electrons, oxygen should have 6. The positive charge kicks an electron off the structure. So we lose a valence electron with the positive charge. So this would be 10 electrons as well. And so then this, just like CO, has to have a triple bond. So we've got to go triple bond here and have a lone pair in each of the atoms. That's just how each of the atoms has 8 electrons closer to it. So we satisfy the octet rule. So we're just using the octet rule as our driving force for these Lewis structures. And then notice that nitrogen's charge would be 0 and oxygen's goes to +1. And now at first glance, you might think, well, this is peculiar because why would oxygen go positive? It's actually more electronegative. It wants electrons more, but it can make up for the fact that it's positive by pulling those bonding pair electrons closer towards itself. But we would still predict oxygen would stay positive and still be positive in charge. It's probably not going to be quite +1, but it's going to end up being a lower magnitude than plus, but still plus in the real structure. And then NO-. For NO-, we have 5 for nitrogen plus 6 for O. Then we pick up 1 electron due to the negative charge. So a negative charge is adding an extra valence electron, so we go to 12. Then this is going to be the double bonded structure. So double bond gives both atoms an octet. So each of the atoms has 8 electrons surrounding it. And then our oxygen here is neutral in charge, so 6 minus 6 for the formal charge. So think octet, you're thinking all the electrons, and then formal charge, you're breaking the bonding pair electrons in half. And so if we break the bonding pair electrons in half, do you notice that nitrogen has 6 electrons closer towards itself, should only have 5 for a neutral charge. So this is nitrogen picking up a -1 formal charge. So -1 for N, 0 for O. If you notice, the sum of the formal charges should go to the sum of the ion. So if you -1 plus 0 goes to the overall charge here of -1. So just like oxidation numbers sum up to the charge on the molecular ion, the same thing here. The sum of the formal charges should sum up to the total charge on the molecular ion. So which bond below is the most polar? Just using the trend of electronegativity. So you shouldn't need the chart for this question. Sometimes you see a question like this on the test, you're like, okay, I want to see a chart. But here we're just really trying to use the idea of increasing electronegativity towards F in both directions. So take 30 seconds to a minute to try to think of which bond here is going to be the most polar. Okay, so the least polar on this group, of course, is F2. So this is the least polar, right? Because it's the same atom. And then the greater the difference of electronegativity, so OF versus NF, NF has to be more polar than OF because it's separated by more. And our electronegativity differences are just going to be greater for NF than they would be for OF. And so you don't want the most electronegative elements bonded to each other for a polar bond. You want the greatest difference of electronegativity. So you want like the least electronegative and the most electronegative. So we get that with NF. And then NCl isn't going to be particularly good in terms of electronegativity difference. In fact, if you were to look at the chart, their electronegativities are about the same as each other. In fact, if we had asked NF, about NF versus ClF, that's actually a tricky question. So if we had added in FCl, its difference in electronegativity is about the same as the NCl, or this difference is about the same as the NF difference. I'm saying distance instead of difference. So the NF difference is about the same as the ClF difference. You wouldn't know that without a chart, but you can know for sure that NF has a greater difference than OF, and then the NCl difference isn't going to be as big because they're both less electronegative than fluorine, so their difference is going to be pretty small. It turns out to be 0 if you look at a chart, but you know that this can't be more electronegative than the NF bond. Okay, so the next thing we come to is for bigger molecules and diatomics, unless there's a simple molecule like CH4 or NH3 that we were doing earlier where a dot structure was helpful, probably for bigger molecules that aren't super obvious what their structures are going to be, we're going to need a more comprehensive way of thinking about how their electrons distribute in molecules. And it's going to be through using these steps here. But the first task is what we've already been doing, summing up our valence electrons, identifying the central atom, and starting to connect things to that central atom, and start thinking about how we want to distribute charge. We're going to see that we start with single bonds first. We try to think outer atoms octets first, and then we kind of shift towards either the octet or the charge of that central atom, and try to think about how multiple bonding might be needed for that central atom. There's something in my head I wanted to say. I think I lost it. But so the contrast here is that for diatomics, we just want to satisfy the octet rule. For bigger molecules, that's actually not necessarily like one of the first rules that we're trying to solve is using the octet rule. It comes up in the process of the rules, but a little bit later in the process. So if you start by summing up, here's what I wanted to say. One way you can look at a Lewis structure, if you ever ask a question like, is this Lewis structure valid for some molecule? If you can count up the valence electrons for the molecule and look at the structure that they should match, that the proper number of electrons should be shown, And if not, then you have the wrong Lewis structure. So one way that you can either support or reject a Lewis structure is if they just differ in the number of electrons that should be shown, then that would be wrong. And so counting up these electrons is really the first step, and it's a useful step because you can use it to rule out a lot of Lewis structures. So if we ask a question on a test, like which Lewis structure is correct, well, you can go rule out all the ones that have the wrong electron counts shown. So you can only try to choose between the ones that have the proper number of electrons shown, and then apply the rules to get the right answer from there. Okay, so we'll come back to this slide. We'll talk about bigger molecule Lewis structures, and then get on with Chapter 8 on Monday. Have a great weekend.